Hello, my name is Vial, and today I will present our latest work on acoustic rigid point cloud registration using Gaussian mixture models. Acoustic perception in underwater environments is challenging due to the low frequency of the acquisition system and multiple and huge sources of noise. When mapping using acoustic range sensors mounted on autonomous underwater vehicles, registration algorithms are needed to establish the displacement between two overlapping scans. A registration algorithm not only lets achieve consistent maps, but also improve AUV data reckoning navigation. In this work, a scan matching methodology, specially suited for noisy and sparse point clouds, is presented. Its case contributions are the application of the Bayesian-GMM algorithm to learn the structure beyond the point cloud, the registration problem formulation using Lie groups, an automatic uncertainty measure for each registration based on the scan structure, a public implementation of the proposed methodology in C++, tests on real data to benchmark our method against the state-of-the-art techniques. Two broad categories of rigid registration algorithms are available. Point-to-point techniques establishes point correspondences and applies the expectation maximization algorithm to solve the registration. ICP is a popular point-to-point technique. Probabilistic methods use GMMs to reach a continuous representation of a point cloud. This probabilistic representation avoids to establish correspondences on data, and the problem can be solved in a single step, avoiding an expectation maximization process. Our work falls in this second category and is developed taking as reference the normal distribution transform algorithm. Our algorithm is divided in three steps. First, the GMM Front-End fits a GMM into a point cloud. Then, the registration method defines a policy for the scan matching problem. Finally, a gradient-based solver specialized for post-optimization is provided. 4 GMM front-ends are provided: NDT, Cummins, EM, and Bayesian-GMM. As it can be seen, the Bayesian-GMM can learn the minimum number of components needed to model a scan, in contrast to the other algorithms that require to fix the number of components. This can be done establishing conjugate priors to model GMM parameters, means, covariance, and weight, as it can be seen in the Bayesian-GMM graphical model. Conjugate priors on weights allows having components without any point assignment without generating any singularity to the inference algorithm. Two registration methods are provided. Point-to-distribution represents the reference scans by a GMM and finds the maximum likelihood of the moving point cloud into the GMM. Distribution-to-distribution represents both scans using GMM and maximizes the L-square distance between both distributions. Many solvers for post-optimization are provided. The optimization is not performed in the special Euclidean group. Instead, it is done in the composite manifold to have the translation independent of the rotation when computing derivatives of the policy. Hence, the sum operator must be defined in this manifold. The solver algorithm is based on an update formed by a step size alpha and a direction d. The step size is found using the line search algorithm based on the Wolf conditions. The direction can be established by one derivative of the cost function using the step descent algorithm or by two derivatives, applying the Newton method. To invert the Hessian matrix of the policy, a modified Cholesky decomposition algorithm is proposed to ensure minimization directions. Here, we can see how evaluations of the second derivative of the policy give information about the uncertainty of the match based on the structure beyond the scan. Results on real 3D data are provided. A 3D scan format by 5,322 points is considered. It was gathered using the Girona 500 AUV, equipped with a delta-T multi-beam sonar mounted on a pan-antil platform, keeping the AUV static while scanning. The performance of the 4 GMM front-ends is shown. We can see that the Bayesian-GMM autonomously learns that the optimal number of components to model this scan is 10. Therefore, this algorithm can adapt flexibly to different environments with different structure. Here, a P2D match with a 72% of overlap applying the Bayesian-GMM is shown. On the left side, the misaligned initial situation is provided, while on the right, the optimized situation is given. It is shown how the algorithm hugely reduces the root mean square error with the ground truth. Here, an animation of the optimization process is shown. On the right side, the evolution of the solver parameters during the optimization is provided. Here, the same situation is registered, now applying D2D with the Bayesian-GMM front-end. It can be seen how the root mean square error is also reduced, but less than using P2D method. Here, the animation of the optimization process is presented. Finally, a C++ implementation of all these algorithms is provided. This implementation is designed and prepared to run in real time in combination with a sonar scanner. Here, the UML class diagram of this library is shown. First, a structure to store a GMM has been designed. The different front-end algorithms are provided in a library of functions. Registration methods and solvers are implemented as inheritances of two temporalized interfaces. This design lets modularly grow the library with other front-ends, methods, and solvers as needed, and can process both 2D and 3D point clouds. Finally, an application programming interface of this library is available, and several usage examples are provided in the library repository. Thank you very much for your attention, and please do check out the open source implementation of our rigid registration method.